Okay, so fundamental theory of calculus. So if I have these functions, let's say this is the fx, and let's say this we have some. Let's say we evaluate any number in between a, b is x. Okay. So let's observe this a to x. Okay. So x is between a and b. Then f. Let me write the f with capital F. Is integrations f is continuous and differentiable on AB. Then the derivative of the big F so every continuous function has antiderivative F. Okay. So this theory will connecting the antiderivative and derivative. Okay. So if we are observing any number, like let's say in between this a, b, let's say just x here, our antiderivative, okay, let's integrate from a to some x here, okay, and let's use another symbols, another variable, not x, to avoid mistake. Okay, so let's say t ft dt. Okay, we can if we can integrate this. Okay, it's integrable, it's continuous. Okay, it's continuous, differentiable. Uh, If you differentiate using ddx of the antiderivative, okay, then if you differentiate the right side of these integrations, you will remove the integrals, and then this will be your fx. Okay. Um, yeah, this definition is really basic for the whole lecture for calculus. So the conclusions is every f, the small f, will have the antiderivative of this big f. Okay? So every continuous functions, they will have antiderivative. Okay? They must have. Okay? So you can say if the function integrable, if you can integrate the functions, then the function is the antiderivative of that function is differentiable. Okay. So if you can integrate, then you can differentiate. Okay. Another notes for the fundamental theory is if functions continues on this interval, and integration of fx dx will be fb minus fa. f is antiderivative of small f. Okay. Yeah, this is the short summary from previous slide. Okay, proof. We'll write some proof here. So proof. Let me write another functions g is the big F. Okay, so easy to say if F maybe will be mixed the small and big F. So let's change the big F to G. So gx is a, okay, and g prime x is fx, and g is continuous on interval AB, also differentiable on AB. And A is X is between A and B. Okay. So proof if, okay, X and X plus H on AB. So G X plus H minus G X. This will be A to X plus H. Okay, let's write one by one. And then this part, I will write A X plus X, X plus H, minus the A X. Okay. And then we get this canceling. Okay. So I will write the next slide. So for H is not equal 0. So G X plus H minus GX. Let's divide by H. This is also 1 over H. Integrations X plus H F t dt. And let the H is positive and F is continuous on X plus H. Then oh, sorry. Let me write the extra value. Okay. Extreme value term. Let's say we have U, V, R on x plus h. Let's say fu is a little m and fv is the big M. And based on the extreme value, let's say this is absolute minimum, this is absolute maximum. And using comparison theorem or property, then M, okay. So if this is so this is M, this is small m. Let's say this is U, this is V. M, H, and let this is x plus h. And this is fu. Oh, let's using dt. Okay. And this is the same as g x plus h. Then let h be approaching 0. Then u will be approaching x, and v is also x. So limit as h approaching 0 of fu is limit approaching x fu. This is fx. Let me copy this part. And then limit they both will be f of x. Okay, so we are using limit to approach the h, and we get the definitions. So conclusion. Using the squeeze theorem, we can conclude that g prime x will be limit h and this will be f of x. Okay, so okay, we can write d dx is equal fx. F is continuous. So if we integrate f and differentiate the result, we will get the original function. Okay. So by using the sum theorem from derivative, okay, using limit, okay. So let me explain a little bit, okay. Explain from here, okay. Okay, so we uh, we determine the if we have some x and x plus h on our interval AB, then first, okay, we use the x plus h and x become our g here. So from gx, we get the gx plus h minus gx, and we also uh, evaluate ax ft dt with x and x plus h. So a to x plus h and a to x. Okay. This part we can separate, become a to x and x plus h. Then we can remove these two. So we can have from here gx plus h minus gx is equal integration from x to x plus h f t dt. Okay, so this is how we prove that this gx, if we differentiate this, it will be fx. That's what we want to prove. Okay. So we get these terms, and then let's divide by h both sides. Okay, because we divide by h, we will get the limit definitions of derivative. Okay, so that's why we are dividing by h, and h should not be 0. Okay, um, suppose the h is positive. Okay, and we are using the extreme value theorem. So we are having some minimum and maximum here for the value of big M and the small m. And let's say we have U and V is our critical point. Let's say this is critical point, where the FU is our absolute minimum value and F of V is our maximum value. And we can use the comparison theorem from previous, the integrations. So we get this part. And if our B minus A is the distance value is h, if this is h, then we can change this B minus A, and A, B become x2 x plus h. So we can having this theorem first, and we get some results here, and it's also remind to this part. So we can approach with two methods, two ways. So this is the first one. Second one is using the extreme value theorem and using the comparison. And you can divide h, and you will bring back the 1 over h here. Okay. And let's change the m into the functions. And based on our first approach, 1 over h integration ft dt is our gx plus h minus gx. Okay. And from here, actually, you can see if we can compute the first part and the last part, it's the squeeze theorem using limit. Okay, limit as h approaching 0. But because in the left and the right, we are having x, right? So we need to define u and v in the x variables. So we can have h approaching 0. So as h approaching 0, u will be x because it's x plus h. If h 0, then u is only x. And v also x plus h, so it's also x. Okay. And using the same limit, both fu and fv, will become f of x. Okay. So using the squeeze theorem, we conclude that the g prime is fx. Okay. So we can write. Okay. So we can write the conclusion. This is the important thing. Okay. Uh, we can write every time you get this definitions. Okay. Integrations f t dt a to x. Differentiate this, you will get fx. Okay. From definitions. So this is the conclusion. Okay. So if we integrate f and differentiate the result, we will get the original functions fx. Okay. So basically, the fundamental of calculus, fundamental of theorem in calculus is just this expression. Okay. This expression. Okay. Okay. Another proof for the fundamental theory is this: if f is continuous on interval a b, then where the f prime is f. Okay, proof. Let let us using G uh, from previous proof. We get the G prime x is fx. So G is antiderivative of f. Okay. So if, let's say, big F is any other antiderivative of f on a b, so we know the fx is gx plus c. we have a constant here. So for the interval a to b, f and g both are continuous on AB. Okay, this is the definitions. And then to prove it, so if we have fx is gx plus c, let's say we have a, b, okay, the interval. So to define this interval, we can take limits each side. So limit here, take limit. So we have x is approaching a from the right side, and also x is approaching b from left side. So let me write, if we put x equal a, so GA is a, f, t, dt is 0, right? So using fx gx plus c, where x is b and x is a, then fb minus fa, it becomes g b plus c minus ga plus c, and this should be g b minus ga, and this will be g b equal a to b f d dt. So this theorem states if we know antiderivative f of small f, we can calculate simply by subtract value of f on can be found by knowing values of x. Okay, so this proof is actually I think not really that complicated. This is just to prove if you have any integrations of small f, then if you have 2 points, at least 2 points, a, b, exact number, then you can process or calculate the integrations just by taking the endpoint of a and b. So as you can see here, if we have the antiderivative f, the big F, is actually our g, and g ga is 0 from our definitions. So we can get the integration of a, b, f, t, dt. So this whole value, at least we can find integration of a, b. Okay. So if we know the antiderivative of these functions and we know the endpoint, then we can calculate the value of whole integrations. Okay. So this is actually what you have already done in many calculations for integration. This is just to prove that this is can be calculated if you have a, b. Okay. And that is also for the definite integral. Okay. A lot of proof, but I think you can just make sure you understand the essence. Okay, the essence. Um, we can also interpret. Okay, I think in physics, maybe you already arrived. So let's say in physics, we can interpret. Let's say our velocity and s is our position at t, okay, at time t. So we can also interpret that our velocity is the integration of the position factor, right? At t, also at t. Then s is, we can say, antiderivative. Okay, we can use that also in physics. So integrations pt dt is sp minus sa. You can also using physics as your to imagine how the relations between uh, s, the positions, and the velocity. Okay. Okay. Maybe to conclude, um, let's say summary. Okay. Summary. So first, if gx is ax, g prime x is fx. And two, if is fb minus fa, where f is antiderivative of f. So f, or if you want to make it similar, we can make it similar if you want. F, or if you want to change to f to g, that's also okay. So these two is the essence for the fundamental theorem of calculus. Okay. Okay. Maybe we will take look back for the fundamental theory later if we have time. But I will just continue to having more integrations. Um, Another thing in integrations is we have indefinite integrals. So if you have integration fx dx without any exact intervals. So we call this indefinite integrals. Okay. We can also write based on our fundamental theorem of calculus. We can write this, and this also this. Okay. And we have some example. If we have x squared dx, okay, for polynomial, I think it's not that difficult, right? We can also write if we have AB, we can write this as we can write like that. And now to compute the integrations, we need several techniques, right? I believe you have learned some of the techniques, but let me review. Okay, if you have um, let's start from the tangent. Okay, let's start from the tangent. So tangent, what is the f prime of the tangent x to the 4? The first derivative of tangent is what? Secant, right? Secant. So let me write using blue color here. Secant squared x to the 4th, and then you multiply with the chain rule for x cubed. Okay. Now you get this idea. You have functions, you have derivative. Okay. Let's reverse. Let's reverse this to the original function. So to reverse, we can have, we are saying antiderivative, or we can just use notation of integral. Okay, let's write the whole thing here. Okay, so what is the integration of this whole thing? If we doesn't know this beforehand, how we compute this? Okay, the idea is we know that secant squared, if we reverse, it becomes the tangent, right? The problem is this part, right? This part. So the idea, okay, based on this chain rule, we can let any variables to change this, the 4x and x to the 4. Okay, okay. Let me write because d dx x to the 4 is 4x cubed, right? If if let's say we have another variables u, okay, if u is x to the 4th, okay, let's uh, derive this, okay. So this will be du, this will be 4x cubed dx, okay. Then we get the terms x to the 4th for x cubed if you are using u, and dx will be 1 over 4x cubed du, right? And if we are pulling this dx inside this dx, okay, 4x cubed will cancel this, right? Right? Okay. So the basic idea of this techniques is by chain rule. Okay? By chain rule. So reversing the chain rule with some other variables. Okay? Let's say the other variables is u. Okay? So we can have this. Let's say this is u, and then this become du. Okay? And if we're just having this simple form secant squared something variables here, we just get this tangent u, right? And tangent u is tangent. Let's put back the x to the fourth. And don't forget plus c. Okay. Also to remind you, if you have tangent u, you plus c here. If the question is not specifically asking about x, it's still correct. It's still correct if you answer up until here. But if you want to change to x4 and you still have plus c, c in the first one and the second one will be different, right? Okay, got the idea? So my suggestion is if you want to make the x, just write the plus c at the very end. Do not write in the middle. The constant will be different. Okay. Uh, Later I will show you why the constant is really important in the integration. Okay. But let's just specifically saying that this whole part we call the techniques is use substitution, or just substitution is okay because you can have v, z, any variables you want. You can usually we'll be using the like u, but you can change with any other variable. Okay. So the idea which you will substitute is based on chain rule relations between all the elements in the integrations. Okay. Okay. Now, if you have integration of x cubed, x4 plus 2, 5 dx. Okay, this part. Okay, with the same techniques. Okay, with the same techniques. Which part you want to substitute? Which part? Hmm? Yeah. Okay. Okay. So you can substitute this, and you can have du is 4x cubed dx, and this 4x cubed, the x cubed will cancel, right? So the idea for u substitutions, you substitute u with x. You substitute this part x4 plus 2 with u, and the important thing is you need to change all x into u. Okay, this simplify the form into u. So let's say we have integrations 1 over 4 u 5 du. Okay, and we get this, and we can easily integrate become u6 24, right? And it will be x4 to 6 24 plus c. Okay. I will give you another example. We have x. So now you have square root 1 plus x squared at the bottom. But it's similar, right? You have x squared, you have x. Maybe you can choose u is the 1 plus x squared, right? It's much more easier. U is 1 plus x squared, and the u will be 2x. And you will be having this square or and you can solve this with the same method for integrations. Okay. But this particular form, okay, instead of using u substitutions, okay, there is a method that I think there it's not in textbook. I call this the method. It's advanced guess. So this method basically came from our idea to differentiate. Okay, you see here x over square root of something, right? Let me try. Uh, if you have square root of x, okay, what will be 1 over 2? Okay, if I have, what will be 1 over 2 x squared plus 1 plus 2x. Okay, okay, you get the idea. So if you know what the form before the integrations, you know the differentiations, you can guess some form. And sometimes this advanced guessing method is faster than use substitution. Okay, you can also use this because it's I learned in some free course in I think MIT. They offer this method. Okay? So it's called the advanced guessing. Let me give you another one. Mm, the easiest one for advanced guessing is, for example, if you have e to the 6x. So because e, if you remember the derivative of e, it will be the same e and multiplied by the chain rule, right? So let me guess e to the 6x and make the derivative. Okay, it will be 6 e to the 6x, right? So your integration will be 1 over 6, right? E to the 6x plus c. Okay. So sometimes the advanced guessing, if you can reverse your equations, it will be faster, more faster than the substitution. Okay. Okay, another one. Uh, Still with e, but let me write x e squared dx. Oh, I forgot the x. Any idea? So you can guess. You can guess. Because always remember, if you have e and e having equation in its power, then its power will be, if you derive, it will be the chain rule, right? You multiply with the chain rule. Okay. So let's try e this part and derive that part first. It will be this, right? Then if you want to make this one, then you need to multiply with the half, right? Multiply with negative half. So the answer will be negative half e. You directly get the answer. Okay. Okay. It's a useful method. Okay. Sometimes faster than use substitution. Okay. Uh, I will move on to, okay, I will explain to you why, okay, why constant or why C is important. So if you have sine x cos x dx, okay. You can use substitutions. You can use, I think guessing also you can find. Okay. So you, can you guess any functions like when you derive, it will be sine x cos x? We have two possible functions to when you derive, it will be sine x cos x. The first one is try this. Okay. Let's derive this and it's become 2 sine x cos x, right? So we can write the answer is half sine squared x plus c. Okay. But we can also have the cos squared, right? Because if you want to derive this, it's become negative 2 sine x cos x, right? So we can have negative half cos squared x. And it's also plus c. But okay, this is why c important. We have two equations, right? Let's say this is c1 and c2, okay, with different c, and let's multiply. Let's adding both. Let's minus sine squared with the cos squared x. So half sine squared x plus cos squared x. So it's equal, or let me write in a, this is C1 minus C2. Okay, so C1 minus C2 is half. So this is also, this is the constant. So that's why when you integrate, you need to write the plus C, okay, plus C, because in some cases you may have uh, several possible integration answer for integrations. Okay, so don't forget to write C. And what is happening with the C? Okay, why the answer is different? Because the C is different. Okay, the C is different. The C1 and C2 is different. The difference between C1 and C2 is half. Okay, that's some notes. Okay. Okay, I think I will stop here. Okay, I will stop here, and next Friday, I will giving you another example for the use substitutions and some example uh, for the integrations. Yeah, some example like I think 8 or 9. Um, and next week we can move to the chapter 6, area between curves. Okay, yeah, fast. But I will give you examples in between. Okay, like examples from this chapter and the next chapter. Okay, so we will, because chapter 5, 6, and 7 is actually uh, related to each other. So I will move forward backwards. Okay. Okay. So I will stop until here, and we will continue next Friday.